Yes, sir.
हाँ जी, स्क्रीन विजिबल है प्रशांत? Okay.
Visible,
Okay. Let us start. In our previous lecture, we talked about the frequency domain analysis of amplitude modulated wave. Before that lecture, we have obtained the expression for carrier wave, modulating wave, and modulated wave in terms of time domain analysis. In the next lecture, we wanted to convert those equations in time domain into frequency domain analysis. Because for every signal, we express the bandwidth for that signal. And bandwidth is in terms of frequency, not in terms of time. So obviously for the practical purposes, hello? हाँ, टेक्स्ट मैंने अभी टेक्स्ट मैंने भेजा नहीं है, ये टेक्स्ट आ गया अब टेक्स्ट।
यस सर, मॉड्यूलेशन इंडेक्स और मॉड्यूलेशन फैक्टर।
हाँ, अब अभी मैंने टेक्स्ट नहीं भेजना था, अभी मैं पिछला लेक्चर आपको ब्रीफ कर रहा था, इसलिए टेक्स्ट नहीं था, ठीक है? ओके, सो इन आवर प्रीवियस लेक्चर वी टॉक्ड अबाउट हाउ टू कन्वर्ट द carrier wave, modulating wave, modulated wave equations in time domain analysis into frequency domain analysis. Why do we want to have frequency domain equations for all these three quantities? Because for practical purposes, we talk about the bandwidth, and bandwidth is in terms of frequency, it is not in terms of time. So obviously for practical purposes, we want frequency equations for carrier, modulating wave, and modulated wave. To obtain the equations in frequency domain analysis, we made use of two things, and these two things were the Fourier transform and sine cosine functions in terms of exponential function. In terms of Fourier transform, we have made use of a frequency shifting theorem. According to that frequency shifting theorem, if we multiply the modulating signal by an exponential function minus j omega ct or plus j omega ct, j is here imaginary number, that is iota. So the frequency shifting theorem will shift the frequency by omega m, and omega m is the modulating frequency. So the modulating signal which was in time domain analysis has multiplied with the exponential function. That exponential function, when utilizes the frequency shifting theorem, then the new modulating signal will become omega plus minus omega m. In the same manner, we have applied the frequency shifting theorem and Fourier transform for other equations as well, and we have obtained all three equations in frequency domain analysis. The spectrum for these equations we have already discussed. Now let us move to the next topic of our syllabus. But before this was the spectrum for these equations in frequency domain analysis. Omega m is here modulating frequency, omega c are the two impulses in carrier frequency. Two impulses means the positive and negative side of the amplitude in the carrier wave. And when this modulating signal is superimposed upon the carrier wave, we obtain the amplitude modulated wave, and the shape of amplitude modulated wave is similar to the shape of the modulating signal. And in the frequency domain analysis, we obtained two bands, lower side band and the upper side band in case of amplitude modulated wave. So this was all about our previous lecture. Now let us move to the next topic of our syllabus, and that is modulation index, and we will do some numericals based upon the modulation index as well. So let us start modulation index. Modulation index may be defined as the ratio of modulating signal to the carrier signal. And we know the carrier signal frequency is higher than the modulating frequency. So the value of modulation index generally lies between 0 and 1. And correspondingly, it is called as no distortion and over modulation, depending upon the value of modulation index is 0, 1 or higher than the 1. Percentage modulation. Percentage modulation is simply the modulation index multiplied by 100, and this quantity is dimensionless. Why dimensionless? Because it is a ratio of two similar quantities, that the modulating signal and the carrier signal, and these signals are represented in terms of voltage or current signals or electric. It is a dimensionless quantity due to same quantities in the numerator and the denominator. Now, with the help of few diagrams, we will try to understand what will be the shape of amplitude modulated wave if modulation index is 0. Modulation index 0 means that we have not superimposed the modulating signal on the carrier wave, and it means the envelope of the carrier wave will not change with respect to time because it has not been superimposed by the modulating signal. So carrier wave will remain same with same amplitude and same frequency, for modulation index is equal to 0. Now let us change the modulation index and what will be its effect. So when modulation index is 1 or modulation is 100%, then it means the modulating signal and carrier signal both have the same amplitude, and this is represented in the above figure, where the amplitude of the modulating signal as well as the carrier are same, and the shape of the amplitude modulated wave for 100% modulation will look like this figure in front of you. 100% modulation. This is 100% modulation. When modulating signal is equal to carrier signal. Now, if modulating signal is lesser or greater than the carrier signal, in that case we will have some distortion due to case the amplitude of the modulating signal and the carrier signal are not equal, and their envelope will distort due to mismatch in the amplitudes of the modulating signal and the carrier signal. You can see the mismatch over here, and this results into a distortion represented by T. Now, how to calculate the modulation index using the amplitude modulated wave? So to obtain this, we make use of the definition of modulation index, that is M, which is equal to the ratio of modulating signal to the carrier signal. And we know the modulating signal is equal to the maximum amplitude minus minimum amplitude in the wave divided by 2. And carrier is equal to maximum amplitude minus modulating signal. If you remember, in one of our lecture, we talked about the carrier equation in terms of a cosine function, modulating equation in terms of a cosine function, and when modulating signal was superimposed upon the carrier, the modulating signal tries to change the amplitude of the carrier, and that amplitude was equal to A plus minus xt. So here you can see the carrier amplitude will be equal to E max plus or minus the modulating signal, that is the carrier signal will change accordingly the amplitude of the modulating signal. So now let us substitute for EM over here in this equation. 3.19 equation is substituted in equation 3.20. So which gives us E carrier, that is carrier wave, is equal to E max maximum minus EM. EM is the modulating wave, which is equal to E max minus E min by 2. So when we subtract E max by 2 from E max, we get E max by 2 plus E min by 2. So carrier will be equal to maximum amplitude plus minimum amplitude divided by 2. We also know the definition of the modulation index says that the modulation index is equal to the ratio of modulating signal to the carrier signal. Now we have value of both modulating signal value as well as we also know the carrier signal value. So when we substitute for EM and EC in the modulation index, EM is equal to E max minus E min by 2. This is the value of EM, and when we substitute the value of E carrier wave, then the 2 gets cancelled in numerator and denominator, and we get the value of modulation index as maximum amplitude minus minimum amplitude in the modulated wave divided by maximum amplitude plus minimum amplitude in the modulated wave. Now let us try to solve some numericals based upon the modulation index. For example, the carrier amplitude after amplitude modulation varies between 4 volts and 1 volt. Now what this number tells us, this number tells us that the maximum amplitude is 4 volt, minimum amplitude is 1 volt, and we have already discussed that the modulating signal, carrier signal, modulated signal, they all are represented with the help of voltage levels or current levels. So in numericals we have to find the modulation index, the power, the current, etc. in terms of Vmax and Vmin. So here Vmax is 4 volt and Vmin is 1 volt. Modulation index is given by Vmax minus Vmin by Vmax plus Vmin, which is, you can clearly see in the last equation 3.22, modulation index is Emax minus Emin by Emax plus Emin. So from in this numerical, we have the Vmax as 4 volt, Vmin as 1 volt. So modulation index will be Vmax minus Vmin by Vmax plus Vmin, that is 0.6, and percentage modulation will be multiplied by 100, that is 60%. Now the next example, a carrier wave is represented by an expression. Here VC, C means carrier, T means time domain analysis, V means voltage. This is a voltage which is varying sinusoidally with amplitude 10 and phase as omega t. Draw the waveform of an amplitude modulated wave for m is equal to 0.5. So here we have given the amplitude, the modulation index. Amplitude of carrier is 10 volts, and we know by definition of modulation index, m is equal to modulating voltage divided by carrier. So Vm from this expression is equal to m times Vc. M is modulation 0.5%, 0.5 into amplitude of carrier. Amplitude of carrier is what? Amplitude of carrier is 10. So we make use of this over here. So 0.5 into 10 gives us 5 volt. V max is Vc plus Vm. V min is equal to Vc minus Vm. So maximum voltage will be 15 volt. Minimum voltage will be 5 volt. And correspondingly, to draw this, we draw an envelope of the modulated wave in such a way that on x-axis we represent the amplitude, and we have to show two amplitudes, minimum amplitude 5 volt and maximum amplitude 15 volt. So this will be the shape of the envelope of a carrier wave is equal to 10 sin omega t and modulation index as 0.5. Now next topic of our syllabus, the expression for power or current in amplitude modulated wave. So generally we make use of the modulated currents and unmodulated currents to find out the power in the electromagnetic waves or voltage current levels when we have a point-to-point contact or optical fiber contact. Then we talked about voltage and currents, and we talk about electromagnetic power when we have pointless contact between the transmitter and the receiver. So power relation between the total power and the carrier is given by 3.44. That is, total power or modulated power is equal to PC, that is carrier or unmodulated power, multiplied by 1 plus modulation index square divided by 2. If we take ratio of PT by PC, it is equal to 1 plus MA square by 2. We know power is given by I square RT. T gets cancelled in numerator and denominator in this equation, and it is equal to 1 plus MA square by 2. So if we take the R as common, that is resistance is common in point-to-point contact through wires or through optical fibers or through electromagnetic wave, we consider the resistance is same at the transmitting and receiving station, and the resistance is also same for the carrier and the modulating signal. In that case, R get cancelled in the numerator and denominator, and we get a ratio of the total current to the carrier current. Total current means modulated current divided by carrier current, which is equal to 1 plus MA square by 2. So in numericals, based upon this, we will be given with one quantity or two quantity, and we will be asked to find the third quantity. Suppose we are given with the modulation index and total current, then we may be asked to find the carrier current. It is also possible that in some numericals we may have two signals, and for one signal some parameter is given, say total current and carrier current are given, and it is said that the second signal is also transmitted with same modulation index. So in that case, we will find the modulation index from the first signal in which total current and carrier current are given, and that modulation index is used in the second signal, and accordingly the quantity which is asked in the second signal will be calculated. So I have here considered both type of numericals. For example, now an antenna is having a current of amplitude modulated transmitter which is given as 8 ampere. If only the carrier is sent, but it increases to 8.93 ampere if the carrier is modulated by a single sinusoidal wave. So here in this example, what is given? Here we are provided with the total current, that is modulated current, which is equal to 8.93. And also the carrier current is given, which is equal to 8 ampere. So what is asked? Determine the percentage modulation. So it means we have to use the power formula to find the modulation index. So this modulation index we have to find. So we make use of power formula, which is IT by IC. IT is the total modulated current. IC is the carrier current, which is equal to square root of 1 plus modulation index square divided 2. If we square both sides, we get this equation, which is IT by IC whole square is equal to 1 plus MA square by 2. Taking MA square by 2 on one side and taking 1 on the other side, we get this equation. Why we are doing? Because we are trying to find the modulation index for the signal for which the carrier has 8 ampere magnitude and 8 ampere current, and total or modulated signal has 8.93 ampere current. So now for modulation index will become, it is simple mathematical algebra, you can easily do it, square root of 2 into IT by IC whole square minus 1. So now we have both the values. We have IT as well as IC. So substituting IT is the total current, that is modulated current, which is 8.93, IC is the carrier, which is 8 ampere minus 1. So if we solve it, we get 0.701. And if we want to find percentage modulation, we multiply it with 100. Now the second question is also find the antenna current if the percent modulation changes to 0.8%. So here again we have to use the power formula. We have to find the current now present current in the antenna. Carrier current remains the same, 8 ampere, which is given. Percentage modulation is 80% now changed. So total current will be equal to IC into 1 plus MS square by 2. And total current now changes to 9.19 ampere. You can compare that when the modulation index was this 70%, then the amplitude was 8.93 ampere in the current, that is modulating signal. And if the percentage modulation is changed to 80%, the magnitude of the total current, that is modulating current, is changed to 9.19 ampere. So in changing the percentage modulation,